we have talked lots about, misses or other hits. So hit and miss, right? So these are complementary to each other. Well, now let us see different types of cache misses, right? So we can categorize, and if you recall the previous lecture, we said, while discussing the cache replacement policy, few misses were written as, aim, rather in red, and few misses were written in black, if you remember that. And then there I mentioned that we'll see the difference in some later point of time in the course. So here is the time, right? Okay. So the first one is the compulsory miss. What is a compulsory miss? That the first access to a block cannot be in cache, right? So you bring block by block to the cache, right? From where? From main memory. When do you bring? Typically based on some request from processor, right? So whenever the first time you are bringing the block, because initially the cache is empty, the cache doesn't contain anything, right? If you bring it for the first time, you cannot expect that to be there in the cache. So that's how compulsorily it will be a miss, right? So that's why it is also called the first reference miss or the cold start miss, right? So typically the literature also says warmed cache, right? So warmed cache means once you bring things to the cache, then the cache becomes warmed up, right? Cache is warmed up. Well, so that's one type of miss. The next miss is capacity miss. So why the name capacity? Because you cannot put everything in the cache. That's not possible. Why? Because cache is a limited capacity. Its size is lesser than that of main memory. And for this discussion, we have assumed that whatever we want to bring, everything is there in main memory, right? If it is not there in main memory, how the things are brought from hard disks to main memory, that will be covered in your operating system course, right? Now for us, for this discussion, we assume that everything is there in main memory, and the cache will contain some portion of that, and its size is limited. So as its size is limited, so that means it contains only limited amount of data, right? So naturally, when the limit exceeds, when you everything, when the cache becomes full, you are supposed to get miss, right? So that's a capacity miss. So another type of miss is called the conflict miss. This is interesting. This says even if there is space in the cache, we'll have a miss, right? Now this will happen in case of direct mapping. Here the mapping is coming to the picture. In case of direct mapping or set associative mapping, right? So it's not possible for associative mapping or fully associative mapping, right? This is also called collision miss. So from these names, you should be ready to make a guess what does conflict miss mean. So it is like, say, let me refer to the previous diagram, right? So let us use a different color pen, maybe. Okay. So we have seen that this block in cache will contain some data. Now a request comes with some address, right? Now what do you do? Suppose there is a set associative cache, okay? So it is a set. Now will you look to other places for this block? if you have a larger cache, let's say, right? Will you look to other places whether there is something over here or not? Will not look. Even if you have nothing in this place, in this set, will not look there, right? We will see based on its set index value, we'll see to this particular place, to this particular set, whether the requested thing is present or not, right? So that means even if there is space in the cache, there can be a miss, right? Because this will be, for this block might come from this or this, right? So suppose this is containing this particular block 1, but the request is coming for 2. That's a miss, right? So that's why the name is called conflicting miss. It's a conflict between this block and this block, right? So that is called conflict miss. Even if there is space in the cache, so the miss can occur, right? And there is another type of miss which is is called, in case of, rather it happens in case of a multiprocessor system. So as to, just to give you some name, that also starts with the C. We see it is whether the blocks are consistent or not, and this is called coherence. So that's miss called coherence miss, right? Anyway, so that we don't need as far as this course is concerned. So for us, we should know these 3 types of misses, right? And we should able to figure it out when this when the miss will happen, on what context, and what kind of miss will happen, right? Okay, so with that, let us come to the last slide. Let us discuss some of the some design issues, or rather some of the things what we normally study in case of a cache memory, right? Some future directions. So this slide will give you some pointers to some future studies of cache. If you're interested, you can of course read that. Normally this is covered in advanced course or architecture course, right, to be precise. So if you're interested, of course you can spend some time to read there, right? Or if you're interested, after some time after the course, you can try to do some project and all. So I'll give some pointer towards that, or you normally study, right? And interested students can look into, of course, in the book or in some other places. So one of the important measure of performance is average memory access time, right? So it's related to time. Of course, with some other, we also nowadays the research doesn't limit to time, but rather the more focus is on power consumption and stuffs like that, right? Which is becoming more important in today's context. Now coming to AMAT, average memory access time. So that means access time. So what do you want? What being a architect or a designer, what do you want? We want the AMAT to be less, because we want lesser access time. But if we want it to be less, how can we make it less? By reducing hit time, or by reducing miss rate, or by reducing miss penalty, or by reducing everything of that, right? Though it is not possible to reduce everything at one go, but yeah, any of the factors over here, any of the terms over here will essentially reduce our average memory access time, right? So these are typically studied in something called optimization technique, cache optimization technique. If you do if you search, or if you write optimization technique in cache, you will get some basic optimization and some advanced optimization. Typically that is there. Or you can also have a look in that the book, quantitative approach, whatever is referred to. Now the question is, how will you do that? So there are various ways to do that. So let me throw some light on some of the things, and I'll encourage you to think, right, before reading the book. From our discussion, from whatever we have seen in the course, I'll encourage you to think. Your thinking might go in totally wrong direction. That is fine, but you should think, and then you can read, so as to match whether whatever you are thinking is correct or not, in the right direction or not. So one can be, let's say, block size or rather cache size. So a typical way, or rather, it's quite natural to think that the cache is placed in between CPU and main memory, so as to keep certain data, some things of main memory. Now if we can make it large, of course, so अगर इसको बड़ा करेंगे मतलब ज़्यादा चीज़ रहेगा, right? So you'll get more things. So naturally we want, if it contains more things, your miss rate will go down, मतलब heat ज़्यादा होगा. So whatever we will want, we can straight away get it from cache, right? So that's a quite natural way to think. But think about a larger list or larger thing, and you want to get something out of that. You must be reading in data structure course nowadays, right? The size increases, then what will happen? You need more time to search, right? Very interesting. Search is one of the important operation as far as any data structure is concerned. So you need more search. Now here search means or hit time, right? So it will increase. So इसको कमा दिया, but hit time ज़्यादा हो गया, right? Along with that, with cache size, so money, sweeter than honey. So it will become, the cost will also increase, right? Because this cache happens to be a faster memory. It uses SDRAM, so faster. So it needs, the cost will increase, right? So then there has to be some trade-off. Coming to block size, so if you increase block size, what happens? So you remember, you want a word, एक word चाहिए, एक block उठा के लाया, है ना? That's what the context. And यहाँ से किसी को कोई एक word है, the requested word. Now the point was, if this is larger, then we'll get a spatial locality. You can take benefit of that. So subsequent, excess might turn to a hit. So that means you are essentially reducing miss rate. Right? Then this is the positive side. So there are negative sides. Why? The block size increases, the number of block you can accommodate in a cache will reduce. That is one thing. Another thing, इसको अगर block, we are bringing the block, अगर block size बड़ा होगा, ज़्यादा होगा, तो वो लाने में जो time लगेगा वो बढ़ जाएगा. That will increase. वो block लाने का time को क्या कहते हैं? Miss penalty. So miss penalty is increased, right? So that is again we need to find a trade-off. So I have just given some, some direction to think. Now you can think about the same thing about associativity, about how many levels of cache we'll put and others. Right? So this is one way to think. Another thing is what is typically done to put some additional hardware. Now you can think how additional hardware, in case of, let's say, you have a read request, you can think in parallel. We have a read request, we have a write request. how additional hardware will help us to to target any of these parameters of average memory access time. Now this is important, writing better code, right? It's always good to write a good code, right? Writing better code means we will incur more number of misses, right? This is something interesting. You can also have a look, right? Okay, so we can go on and on. So this, as I previously told, that this slide is just about to give you some hint and some pointer towards the future study regarding the cache, right? So with this, we have come to the end of our course, or the cache memory and the course. Of course, I should thank you, because I have seen that many of you have have followed the video lectures and you are posing questions, so that is good to see, right? Hope everyone does that, right? And you can have a better discussion in the course website, a good platform. Now, saying that, if you have still any doubt, please feel free to write, of course you can use the course website, or you can write to us. We'll be more than happy to help you, and hope you are fit and fine this time, right? So with that, let us wrap up the CS 104 lecture, right? Hope to see you in the college soon. Thank you.